So hopefully we have a pretty good handle on the fundamental identity. Now let's take a look at some other series that we might see. Again, our end goal is to then be able to utilize this side of the equation to help us solve for those coefficients quickly and easily. So we still haven't gotten to that part yet. We're just looking at those tools that are going to help us to get there. This is called a geometric series, and it's geometric because we're taking some value to the power of 0, of 1, of 2, etc. So notice what I've done here. This is the summation from 0 to n of 2 to the n, and then this is 3 to the n, and this is 4 to the n. And if you'll notice what's happening over here, what I'm asking is, can you write the general form, meaning replace 2 with, say, a or x, and tell me how I could generalize the geometric series. So once you feel like you have gotten to that point, then let's move on to what the solution is. So again, by replacing the value of the base with x, what I'm looking at then is this, which is x to the n plus 1. Remember, n is that upper bound of our series, minus 1 over x minus 1. And what we're going to do is we're just going to rewrite it a little bit differently by multiplying by -1 on top and bottom, which is totally legal. Multiplying by -1 on top and bottom is the same as multiplying by +1, which is fine. And so I come up with this. I have 1 minus x to the n plus 1 over 1 minus x. And I do want you to keep in mind that this does have an upper bound of n. In our previous examples, we were always looking at through infinity. This will have an upper bound. So it's important that it has an upper bound because obviously I can't replace n with infinity in this particular situation. So again, this is for a geometric series, a finite, which means that it ends. It ends when our index reaches n, geometric series. So let's look at getting ourselves one step closer. We still haven't reached the point where I'm solving for x to the 28 g of x. And I'm not going to get to it on this slide either. But I'm going to get you a step closer. So we're going to use what we know about the finite geometric series. And I'm going to take a question that we first looked at in video 9.1. So again, if you didn't watch that video, I would maybe go back and watch it, or if you don't recall this question. We were writing a generating function for basically adding 4 integers to get a sum of 28, and we know this is where we want to end up. And previously, we got to this point and we stopped, because we said the first term had to be between 0 and 10, so I've got 1 all the way up to 10. This is x to the 0, because I could have 0 of them. X sub 2 is greater than or equal to 12, so we started at 12 all the way up to 28. But really, I wouldn't have had to stop at 28. This one could just continue forever because it's not actually bound by anything. And then these guys go from 1 to 9, and so I started at x to the first. So that's where we ended before. Now I'm just going to take it a little bit further, and when I say a little bit further, I really like this. I wanted to start with x to the 0. So I'm going to do some factorization. First guy I didn't have to factor at all because it already started with x to the 0 or 1. But for the second one, if I take x to the 12th out, that leaves me with x to the 0 plus x to the first, etc. And again, I can just use that as a infinite series. That's going to make it easier on me. And the reason that I can write it as infinite is even though I'm looking for x to the 28th, there is no restriction. Like this one has a restriction that says you have to stop at 9. This one has a restriction you have to stop at 10. This one does not. It's just saying it's bigger than 12. So that's how I could rewrite that as infinite. Then I'm saying I really want this to start at x to the 0, so let's take an x to the first out. And again, you can just write that as x or x to the first. So what has that done for me so far? Well, I know that this is a finite series that follows this pattern. that we just learned. 1 minus x to the n plus 1 over 1 minus x. And this guy is finite because it stops at 8. Again, using that same pattern. And this blue guy in the middle, what's that? That's an infinite series, which was the easy one, the fundamental identity, 1 over 1 minus x. So of course the next step is, let's put that x to the 12th on top. Let's multiply by that other x as well. Let's just stick it on top of this one. And so this is how I would write that generating function. And again, am I here yet? No, not yet, but I'm going to get there. But that's the next step in what we would do.